this is when push comes to shove. And we've got two forces, 600 newtons and 30 newtons, acting opposite direction on block, frictionless surface. Frictionless, so no other. If we were doing the force diagram, what other forces would I have on this block? No, because no resistance because it's frictionless. Well, is it near the planet Earth? Yeah, assuming so. So what force must it have on it if it has mass and it's near the planet Earth? Gravity, otherwise known as its weight, right? So the force of gravity down, and that would cause what other force? The normal force. But do those are up and down, vertical. Are they contributing at all to our horizontal motion here? No, so we don't. That's why they don't bother putting them on the diagram. So, but those would be there. And I start at x minus 0.4 meters. And sometime later, the block is moved to a new position, 0.2 meters. And they want to know the work done on the block moves from this to this. So, in my y, I'd want to show that I understand something along the lines of work is done when a force is applied in the same direction as motion. And I might put after that distance. I could use motion or distance. All right. And I might also, just looking forward on this problem, I noticed that they're going to ask me a couple things about work. They're also going to ask me about net work. So I'd want to show, I'm going to go back to my y to show my understanding of network. And they also asked me about the change in the kinetic energy as the block moves. So I want to show that I understand those two parts of the question also. So I might say, let's see, something along the lines of the net work is the total work and it is done by the net force. And that kind of gives me the option of either looking at it as the total, as all the works combined, or looking at it as what is my net force on the block and figuring out the net work done. And then the last part I should have in here is the net work causes the kinetic energy to change. So if we were to cite a law, it would be that's the work kinetic energy theorem, but it's what the network causes it to change. So let's from our equation sheet, we're going to work be down here. We're going to have work is force parallel to the displacement. We're going to have net work is the change in kinetic energy. And those are the only two that we need. All right. So the way I'm going to use those for part A, I'm using work equals force parallel, displacement parallel. And they want to know for part A, work one done by the block by the force magnitude F1. I'm trying to figure out how they put in that subscript. Block moves from this to this. Express your answer numerically in joules. So joules I know is newtons times meters. Got to make sure I'm in newtons and meters here. I've got 60 Newton force moving it from that. So let's do that. So I've got, I can, now, which way do you want to do it? Do you want to say, okay, in my head, I can figure out the distance from negative 0.4 meters to 0.2 meters, or do you want me to put it in mathematically how you would do that? How far is it from negative 0.4 meters to 0.02 meters? 6 what? Okay, so 0.06 meters? Is that okay with everyone? Can you do that in your head? Okay. So, now of course I need to remember the 60 newtons. So my work is going to be my 60 newtons times my 0.06 meters. Do I need a positive or negative on that? No, because it's a scalar. It has no direction. You guys are animated this morning. This is good. This is good. And then I go on to part B. Of course, you do the math there. But part B has same thing, but now the 30 Newton force. So using the same formula. This is work 1, this is work 2. Yay! Any questions on A or B before we go on to part C? Oh, we're good? All right. Part C. What is the network done on the block by the two forces? Now, which would you guys prefer to do? Figure out directly the net force, or figure out the net force and therefore the net work, or figure out the total work done? No. Total work? Okay. So to do the total work, what I need to say is, okay, which of these two is adding to the energy, and which of these is taking away from the amount of energy it has? So it's moving towards the right. So F1 is going to be increasing its motion, so adding to the amount of energy it has, while F2, since it's directed to the left, is going to be taking energy away from the block. So whatever work F2 produces, I'm going to call that negative because it's taking energy away from the block. And I'm going to call whatever work F1 produced positive because it added energy to the block. So not direction, but adding or taking away energy from the block. So my work net is going to be the work from 1 plus the work from 2. And I said, and so I have W net. Work 1, we said, is adding to the block, so that's going to be positive, what is that? Let's see, 36 joules minus 18 joules. And so I'm going to get a total work of 18 joules on my block. Yes? Okay. And then going on to part D, I'm going to use from my equation sheet here again, that W net is a change in kinetic energy. And then looking at my problem, they want to know, determine the change in kinetic energy. Oh, okay. So the change in kinetic energy, 18 joules equals change in kinetic energy. Any questions on any of that before we go on to a different problem? All right, so we're going to do 6.114. And this is one of the power problems. So right away in the Y, you need to show that you understand rabbits. What do you got to understand right away to do this problem? Well, it would be good to understand that unit, but I wouldn't go into too much research. It has to do with when a gentleman named Joule was showing that his steam engine could work in the coal mines as well as teams of horses. So he came up with a unit to equivalent the two. So he could describe how much power his steam engine could produce and have the people who wanted to pay him money equate that to how many horses they would have to use and make it easy. Horsepower, it's kind of outdated. But it's also kind of like feet and yards are outdated, but we're sticking to months, right? But I don't think you have to understand the unit too much to do this. What concept do you really need to understand to do this problem? Power, right? Power. So you need to show that you understand that power is the rate work is done. And then you need to understand, as a couple you just said, energy and work. Okay? And so I might put something like, I am doing work to increase my PE as I go up the stairs. Just like that lab, the interact that you guys did pulling the cart up the ramp, the work you did on the cart increased the potential energy gravitationally of the cart. So I might even throw the word in here, gravitational. And that's probably a good coverage for my Y. You okay back there? All right. And so my how side, let me just look and see what I'm figuring out again. I'm going to remember that 1 horsepower. I'm going to find my answer in watts and then convert it to horsepower. So I'm going to then peruse my equation sheet for, why don't we capture this? Bring it over rather than me writing it. For my power, and I'm really going to use that power is the change in energy over time. I'm going to pick that part out of this chain equation. Remember, power equals each of these, and each of these equal each other. So I'm going to use that power is the change in energy over change in time. In this case, as I said, the work I'm doing is changing my potential energy gravitational per time. Then I'd flip back to my equation sheet and say, oh, my potential energy gravitational is mg. What's mg? I'm really glad I added those 6 problems on the bottom. It's the weight of something, yeah. It's the gravitational force on it. Oh, I'm so glad I added those 6 so you get lots of practice. Mg is the weight or the force of gravity, whichever way you want to say it. Which way do we want to say it? Weight? Okay. Let's try it again then. Drew, lead us off. Tell me, what's mg? Oh, 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 oh. Because Michael, and Pat were not paying attention. So I was hoping that they were, and I was just reading their body language wrong. Michael. We're going to go back over to our saviors. Victoria, what's mg? Wait. Should I cast it back over? Let's see. Pat, what's mg? Wait. All right. Friday morning, we're getting it. So, for my potential energy gravitational, I'm going to use this. So, my power is going to be my weight mg, the height, and which one am I changing as I go up the stairs? My weight or my height? Height. And the change in time. And now I know all of those values. So let's grab them. Let's see. They tell me my mass is 82 kilograms. What planet are they assuming that I'm on? Earth. All right. So I'm going to assume that also. So what was that, 82? That's Friday. There you go. Okay. So I'm going to have 82 kilograms times 9.81 newtons per kilogram. And then the height that I go up is 3 meters. What was the height of the stairs you guys climbed yesterday? 2 meters? Yours was 3? Okay. Yeah, really, it does. And then I do that in 10 seconds. So my change in time is 10 seconds. And that gives me my power. I'm going to calculate. I'm going to get what that is. So I can then convert it. It's hot in here. I always hold off until I get a final value to do my sig figs. I'm going to do 82 times 9.81 times 3 divided by 10. And I get 241.326. Joules per second. And a joule per second is also known as a watt. So a W. And then they tell me for every horsepower, there's 746 watts. So the way I think of doing conversions is I take whatever number I have, I multiply it by the number 1, since I don't want to change how much stuff I have, and I put what I want to keep on the top, what I want to get rid of on the bottom, and there's 1 horsepower and 746 watts. That makes the number 1, right? Yep. Because anything over itself is the number 1. And then I just do the math with that. And I figure out, well, that equals blank horsepower. And that should give you your problem. On this one, did people notice they wanted your answer in kilojoules and kilonewtons? So like if you got an answer of 15,000, what would you enter? 15,000 newtons, what would you enter? 15. 15, because you move it 1,000. All right, thanks. Shane. you are the lucky recipient. Okay. All right, so if the bicyclist has inertia and it has velocity, what type of energy or speed, what type of energy must it have? Kinetic energy. And so if it stops, therefore it doesn't have kinetic energy anymore. So what we're looking at is the work to change the kinetic energy. So that's kind of where I would start here. What was it, 9.3? So the work on the bike, I'm going to call it, will change its kinetic energy down to 0. And I'm probably going to add in here, just make sure that my reader understood. Work is created when a force acts through a distance. Probably all I need for my y, I would say. All right, so I'm going to, the brakes are doing actually net work on this, so I'm going to go back and use the W net equals the change in kinetic energy. And I'm going to start off by expanding out. Now let's see if it's changed. Is it initial minus final or final minus initial? Final minus initial. So KE final minus KE initial. And, oh, I know the final, that's 0. Minus KE initial, which would be 1/2 mass speed initial squared. Am I going to come out with a positive or negative answer? Negative, but my guess is they're going to want the positive because they just want the magnitude of the work. But we'll see. I mean, I get 10 tries, so I'm going to try the positive and then try the negative, and as long as I didn't mess it up. So, and let's see, what are my values here? 65 kilograms. Who rides his 9.8 kilogram bicycle? Oh, so they both have kinetic energy, right? So I've got to combine their inertias to get my total for my person on the bike. Oh, I didn't see that at first. So 1/2, my inertia is going to be 65 kilograms plus 9.8 kilograms. And my speed for me was 14 meters per second. And that's squared. Let's see what I get. So 0.5 times parentheses 65 plus 9.8 close parentheses times 14 squared. And I get 7,330.4, which I'm going to report as 7.33 kilojoules, because this is in joules. Let's see if I got that right. I hope I did. But it is Friday, after all. Let's see if they wanted the negative. Yeah, so they did want the negative. They didn't want just the magnitude. They wanted you to realize that the work was reducing the amount of energy the object had. And then part B, what is the magnitude of the brake force? Oh, here they only want, they don't put a negative in part B, because it says magnitude. So they only want the number there. So for part B here, bless you. And we'll use green for part B because green for B things. Here we're going to use the force. Our definition of work. I know my work 73330.4. Make sure they give me the right thing. Oh, wait a minute. Huh? They give me the time. Do I have any equations that involve work and time? Power does, but they're not asking me about the power, right? So this involves, maybe I better figure out how far the bicyclist travels while stopping, right? Before I can do this, because I'm looking for the parallel, but I don't know what this distance is. And this is joules. So I'm going to, on a little side note over here, I need to figure out how far this bicyclist traveled going from 14 meters per second down to 0, right? And let's see, what else do I know? Let's look at some equations. I know the time, right? And I want to know how far. Also, I could figure out, I could figure out the acceleration, right? And then I could use other forms. Yeah, I think that's what I'm going to have to do. So I'm going to have to go, okay, acceleration is change in velocity over change in time. So in this case, the acceleration is 0 minus 14 meters per second over my time. What's my time? 4.5 seconds. And so I get an acceleration of negative 14 over 4.5 meters per second squared, right? Then I can use the D equals D naught plus V initial T plus 1/2 A T squared. Actually, yeah, that works. And I'm going to say we started at 0. When we start moving, we're moving at 14 meters per second. Our time, 4.5 seconds, plus 1/2 times 4.5 squared. And I'm going to get an answer for D. Let's see. 14 times 4.5, all plus 0.5 times, parentheses 14, divided by 4.5. Oh, it's definitely some simplification I could have done there. And I get it moved 94.5 meters. And that's what I'm putting up in here. And then dividing and finding my force parallel. So let's see if that works. And it should. get 77.6 newtons. But remember, I got to do that in the kilonewtons. I need to pause this so I can save it before the next class.